So today we are going to start with the last part of the data plane, that is middle boxes. Okay. So what is a middle box? That's what we need to start with first. So according to the RFC 3234, middle box is nothing but it is kind of an intermediary device which performs functions apart from what a normal router performs. So it performs some additional functions, some different functions than what a router performs in general. Okay, between a host and a destination. Source and a destination. Okay, so if I have to say what's a middle box would be some kind of a device between any two hosts any two hosts, basically a source and a destination pair, and that middle box will do some extra work as compared to what a router does in general. Okay, so by now you must have studied a lot of concepts where the tasks that are being done are much different from what a router in general does. The task of a router is nothing but, if there's a packet that is arriving, you check the destination address, and then using the routing algorithm and the entry or the um, content of the forwarding table present, you forward the packet to the corresponding interface or corresponding output port where the from where the packet will be moving towards its destination. Okay, that's the task of the router. Now, if something extra is done on the packet apart from this, and the device which does this extra work, that is called as a middle box. Okay, so the source and the destination pair, they may or may not be aware that whether there is a middle box in between. Okay, so I think with this it will become more relevant to you and more understandable. See, NAT. We have already studied about NAT, network address translation. So the NAT router that we were speaking about when we were studying NAT, that acts as a middle box. Okay, how? Of course, it does something other than what a router in general does, right? It will basically try the or do the translation of the addresses. Okay. Now, one more thing that I said is that the source or destination host may or may not know about that there is a middle box in between. Okay. So the outside world, of course, may not know or does not need to know actually that there is a NAT router, or the destination address to which it is sending is actually of a NAT router and not of the exact uh, destination host. Okay. And if you think from the other way around, that is from the organization or from the institution to the outside world, in that case also, as a user, you are not bothered about whether there is a NAT router or whether your IP address is the exact IP address or not. Okay, so the hosts which belong to the organization which has a NAT router, in that case also, they may not know that there is a NAT router or there is a middle box in between. But the middle box, which is the NAT router here, that is basically doing or taking all the responsibility and doing all the translations that are required. Okay, so in the internet, we have middle boxes everywhere. One example is of NAT. You can have it in your home network, in cellular networks, using cellular network also, and in institutional networks also. Another is, firewalls. Okay, so you have corporate institutional service providers, ISPs, etc. There also you can the middle box can act as a firewall, or in the middle box, if you have certain, like what we did in the class yesterday, that if you put certain conditions, and then you can actually implement a firewall in that case. Okay, our match action pairs that we were doing in yesterday's class, right? Then there are load balancers also. These are also the tasks of middle boxes. Okay, so these are generally there in corporates. They are there with ISPs, that is service providers, data center networks, and even mobile networks. And you can also have middle boxes, which are application depending upon your application. Okay, so you can have application specific middle boxes, um, depending upon what your service providers want to give to their customers, for institutional networks and for CDN, that is content delivery networks. And of course, you can also have caches on the internet, which will be a form of middle box. So caches can be there with the service providers, with mobile networks. You, I don't know whether you have heard the term of mobile edge computing or not. So we do have caches there, and then you have, of course, CDNs, which definitely are dependent upon, or which use the concept of having caches to deliver the content to the corresponding users. Okay. So on the whole, if you want to know what is a middle box, the basic concept is that it is simply a device which is lying between a source and a destination pair, or a number of sources and a destination pairs, and those are basically acting as, or the device basically supports actions which are different from that of router. They can be network address translation, they can be for they can be helpful for acting as firewalls, load balancers. Caches can be considered as a middle box, and there can be some application specific actions for which also we can use the help of middle boxes. So initially, middle boxes were considered to be proprietary hardware solutions. Then we have moved towards white box or hardware implementing an open API. Okay, so this is nothing but you are just trying to move or give a API based solution for the task that you are going to do. Okay, instead of having a hardware based implementation, you just have a API based solution. Okay, so how can you provide this? You can provide this using programmable local actions via match plus action pair, which we did in yesterday's class, right? So you can have programmable local actions using match plus action pairs in your corresponding forwarding table, and then this will move towards a software based solution rather than a hardware based solution that we are basically providing. And this is the basis of what we generally go for when we are talking about software defined networking. Okay. And so this comes here that SDN, or software defined networking, logically, it just divides the entire network as a centralized control and the hardware which is there near to the hosts. Okay. So in the core network, you have the routers. So if it is independent, if the routers are all independent of each other and they are working with the forwarding table and routing table with which is lying with them, in that case, it is a solution where each of the routers have to maintain the information, they have to get information of all their neighbors, and then they have to work each time there is a packet, right? Each time there is a packet, all of the routing and forwarding tasks have to be done in a distributed manner with each router. So each of the routers now has to have some kind of intelligence. Whereas when it comes to SDN, what can be done, as we have already studied in the previous classes when we were talking about what is SDN and how it works out. So there, what we have a centralized control. So logically, it seems that we do have a centralized control where all of these decisions regarding forwarding of the packet can be taken up, and there's no need to further take up the actions such as advertising about whatever the network whatever changes are there in the network, what has to be done with a given packet. So those information are not required to be exchanged because there is a centralized control which is already there. Okay. And where's this centralized control happening? So this happens at either a private cloud or a public cloud. Okay. So for implementing this concept of SDN, middle boxes play a very important role. Okay. Again, network functions virtualization or NFV. I think you guys have seen this term a lot by now. But anyways, this is nothing but programmable services over such kind of a white box networking, computation, and storage. Okay. So this is what NFV is, and middle boxes are also helpful for supporting these. So basically, what we are looking at here. Okay. So when it was this has been taken from a paper. Okay, so this is just a conceptual format of what happens in the network. If you see here, you see it is just simply the layering: application layer, transport layer, network layer, functionalization, and then you have the link layer and file, okay, physical layer. So what is it? So this IP, it is considered as a thin waist. Okay, so this network layer is actually considered as the thin waist of the internet. That means everything is it is just the central point. It is the crux of what's happening over the internet. Okay, so this IP protocol is actually the thin waist of the internet. So the all the above layers and all the below layers, they are basically handled or balanced by this particular protocol. Okay, so no matter what it is, it must be implemented by every internet connected device. Okay, on. Of course, we do have many different protocols related to all the other layers, but IP is the one that stands tall in between all of them, and it is the one that basically uh, should be there, or it is the crux which actually supports internet. Okay, now if we have middle boxes, okay, if we have middle boxes, what else can be supported on top of this? NAT, caching, firewalls, and NFV. All right. Hmm. Anyways, this is just the architectural principle of the internet. Okay, it is simply saying that what are the three cornerstones. One is you need simple connectivity, you need the IP protocol, and you need intelligence or complexity at the network edge. Okay, so let's just go through this once more. Simple connectivity is you need to have very simple way of connecting from one host to another over the entire network. That is one. Number two is that your IP protocol. It is the crux. It basically balances all the other layers. So IP protocol is very important. And the third one is intelligence at the edge. That means when we say at the edge, that means are the edge routers or the edge hosts. So when you look at the, if you remember the figure that I have always followed, that means the core network is there and there are various devices which are getting connected to the edge routers. Okay, so if you see all the complexity, most of the complexity is at the edge. One is how do you connect to the edge router? So you have wireless connectivity, you have wired connectivity, various types of technologies which will basically help a device to get connected to the edge router. Then you have how do you address all these different hosts? Then how do you get or how do you find out the destinations of these end hosts? Whatever applications they are using, correspondingly, what are the corresponding application layer protocols, corresponding transport layer protocols, and many other things. Okay, so most of the complexity is at the network edge. Okay, so these are the architectural principles of the internet. Now, when it comes to middle boxes, actually, there's a very good lecture on middle boxes. It's actually a presentation basically from Stanford University, and there's one more lecture also. Um, I will basically what I'll do is I will upload the links of these two lectures on middle boxes. Okay, if you want a little more, if you are enthusiastic about middle boxes and if you want to see a little more on what middle boxes are and how they are basically balancing the internet. So in that case, you can simply go through these links. These will be good references for you. Okay, so I will upload the links for those two. You can follow them. All right. So I have changed the presentation. I think that you can see this Dijkstra's algorithm now. If not, let me know. Okay. So today we are going to start with control plane. We have already done about or we have already studied about data plane for this course. Now we are going to study about control plane. Okay. So we had already started with the routing algorithms and we had studied about link state algorithms, right? And this is what we are going to start first with link state algorithms. Okay. So what's link state algorithm? Let me just go ahead and just give a recap to you. So this is what wait, wait, wait. I'll just tell this. Just a second. Okay. So link state algorithms are basically those algorithms where the state of the entire network is known to all the hosts belonging to the particular network. Okay. So every host knows about the state of every other host in the network. So if you think that there's a centralized control, in that case, you can think of like, okay, in this situation, every host can know every other host's information. So that is link state algorithm. Then another classification that we have is distance vector algorithms. Okay. So what are distance vector algorithms? These are nothing but decentralized algorithms where with the help of an iterative process, a host gets to know about its neighboring, about the state of its neighboring hosts. Okay. So here neighboring host would be that host which is directly connected to the current host. Okay. If somebody is connected via several hops, then you don't know the information of those other hosts directly. So what you do, if a particular host A is directly connected to other hosts like B and C. Okay. So from B, A will get the information of all other hosts which are again directly connected to B. From C, A will get the information of all other hosts which are directly connected to C. So like that, every host is actually collecting information of all other of maximum number of hosts that it can from its directly connected nodes. Okay, so this is known as distance vector algorithm. All right. Now the question that arises is which kind of algorithm should be used in which case. So we have seen that it depends on what is the kind of network that we are currently looking at. If in your network the routes change very slowly over time, then you call it as a static network. Okay. So in that case, I think you know the answer better. Which kind of algorithm should be used, and when it comes to a scenario where routes change very dynamically, in that case, also you can actually use a kind of algorithm, whether it can be link state or distance vector, that I think you should think about. Okay. Remember, in link state, all the routers have to have complete information of each other, and in distance vector, the information can be advertised to only the directly connected neighbors. Okay. Now, let's check the next part. So, as a link state routing algorithm, as the basic one, we had started with Dijkstra's algorithm. Okay, so as I've already mentioned, it's a centralized algorithm, and all the states or all the information of nodes in the network is known to all the other nodes. Okay, so how it can be known? It can be known via link state broadcast. That means each host broadcasts its information to whatever information it has. It broadcasts that information to all the nodes in its neighborhood. Okay, so that all the nodes have the same information. Right. Next is that once all of this information is there, Dijkstra's algorithm helps to find out the shortest path from a source to all the other nodes in the particular graph. Okay. So essentially, it will give you the forwarding table for that particular node. Okay. So it is an iterative algorithm, and these are the notations that we will require for representing the Dijkstra's algorithm. So CXY is the cost from node X to Y. So cost we had already seen in the last class when I was talking about Dijkstra's algorithm. I had told you that in the network when we are looking at the cost factor, it can either be the link capacity, the bandwidth that is provided, the latency, or what is the number of hops, etc. Okay, so those can be considered as the costs. All right. So here, if a node or if a pair of nodes are directly connected, then you have the cost as the edge weight, and if they are not directly connected, then the cost is given as infinite. Okay. Then you have dv, which is nothing but the current estimate of the cost of the least cost path from source to the destination being v. And PV is the predecessor node along the path from source to V, and N dash is the set of nodes whose least cost path is definitely known. So this is what the algorithm basically looks like. Okay, so initially you just compute the least cost path from so U being the source node, from U to all other nodes, and then you basically try to find out from the adjacent nodes of U, that is U initially knows the direct cost path only to its direct neighbors. So from the directly connected nodes of U, it finds out the cost. Okay, the cost that will be required for all the nodes which are there in the graph. Okay. So we do have a loop here because it is an iterative algorithm, as was already told. Okay, so then we generally just find out that what is find W, which is not in N dash. Okay, N dash being this node U, such that the cost to W is minimum. Okay, once you visit that node, you simply add it to N dash so that you don't visit it again, and then you update the cost from U to the node V. Okay, how do you update it? So this is important. The cost is updated like this: D of V is equal to minimum of D of V comma DW plus CWV. Okay, so you find out that if so, this is nothing but you just try to find out that whether there is a direct connection to the particular node or not. If there is a direct connection, then what is the cost? If you go to that, you can visit that node via some other node, then what is the cost? That will be given by DW plus CWV. Now, whatever is the minimum out of the two, that will be considered as the cost for DV. That is to visit from U to V, that should be the cost. Okay. So essentially by doing this, what will you get? You will get the way to visit, or the shortest path to visit from you to the nodes present in the graph, to all the nodes present in the graph, that will be the least cost path from you to any other node present in the graph. Okay, so let's see how this Dijkstra's algorithm works out. Okay, you already have seen in your algorithms classes how Dijkstra's work, so I don't think I have to explain the algorithm, the previous pseudocode much more. So let's just see how this works out in a pictorial manner. So you start with the node U as the source node. Okay, so in N dash you have U. Okay, now you try to visit, or you try to check out that if you want to visit all the other nodes present in the graph from U, okay, what is the cost that you get? Okay, so one by one, iteratively, we will try to find out. So check this here in the graph that has been given. If you want to move from U to V, there is a direct edge from U to V, and that is having a cost of 2. Okay, so you got the cost as 2 here. All right. Then now similarly, you just get to W. Okay. Now W, if you see the connecting edge, the direct connecting edge to W, that has a least cost path, or sorry, that has a weight of 5. Okay. So that is there, and then also if you move from U to V and V to W, that's also going to give you the edge weight of 5, the cost of 5. Sorry. So you choose the this one, the direct edged one, and then you put it as 5 comma U. For X also has a directly connected edge with cost 1, and you put it here. All the other nodes which are not directly connected to U are given the cost of infinite. We have already seen that. Okay, so this is the initial step. Okay, now we'll go one by one. Okay, so let's see. Let's start with, so these three already have direct connections. Okay, U, 2U, and 5U. Okay, for U, V, and W. Okay, and these seem to be the least cost ones. Okay, now let's go to the X, to the node X. Okay, so you already have the minimum one here. Okay, so how do we choose in Dijkstra? You first go ahead and take a look at this row. Okay, you check which one is the one that costs the minimum, which node costs the minimum, as you move from that source node to the corresponding node. Okay, so from you, the one with the minimum cost is X, so you put X here. Okay, then you start finding out the next part. So this is the correct, I mean, this part is what you are considering as the final one from U to X, because it is the minimum one as of now. Okay, now let's get to the next part. So you have gone from U to X. Okay, now if you want to go to V, okay, so even in this case, what is the minimum cost that you will get? You can go from U to V either directly, or in this case, because you are traveling until X, if you want to move from X to V, in that case, using the formula that we have, that is dV equals to minimum of TB comma dA plus CAB, you will still find out that this is the, um, if you go from U to X and X to V, it will cost you 3, and if you go directly from U to V, it costs you 2. So you will of course take the minimum and 2 comma U. Similarly for W, if you want to find out, okay, you had a direct connection from U to W which was costing you 5, but if you go from X, then U to X is 1 and X to W is 3, so the total cost becomes 4. So that one is the minimum one, so you consider 4 here, and this is via node X. Okay, X to X is of course not there, and then you go to Y. Okay, so Y is here. So basically you are now tracing all the nodes that are connected to X, right? So you have traced W, you have traced V, and now you are tracing Y. Okay. So from you of course did not have any direct edge to Y, so it was infinite. So therefore, if you want to go from U to X to Y, you will find out the cost is 2. And if you take this as minimum of dv comma dA plus CAB, then in that case, of course, it will be written as 2 comma X. Z is not connected to X, so the cost will still remain infinite. Okay. So now among this, which one is the minimum cost one if you have to go via X? Then it is Y here. Okay. So you put Y in N dash, and then again from Y you check that how can you visit all the how much cost will it incur if you want to visit the nodes which are connected to Y. Okay. So now let's check. So for V, of course, it still remains that 2 comma U is the minimum one. For W, okay, now for W, what happens? What was the previous cost that you were getting? That it was 4 comma X, right? Now if you go via Y, it is U to X is 1, X to Y is 1, and again Y to W is 1. So it becomes 3 comma Y, which is less than the cost of 4 comma X. So in that case, you take it as 3 comma Y. Among this, which one is the minimum? U is the minimum. The cost for V is the minimum with 2 comma U. You put V here and then correspondingly you go ahead. Okay, you try to check that what's the path that you should take for the corresponding adjacent nodes, that is W and Z. You find again the minimum cost one, which is W, that is 3 comma Y, and then put it in the end at N dash, and then try to find out what is the cost of the adjacent nodes. Find Z as 4 comma Y, put it, now it is the only one that is remaining, so now you put it as put it in the set N dash, and then that's it. Okay. So what are you getting now? If you see this in this graph, U to V, this is the least cost path, U to X, and then Y, W, and Z. This is the least cost path that you get from U to all the other nodes present in the network. Okay, so this is how Dijkstra's algorithm works iteratively to find out the shortest path and or the least cost path from a host to all other nodes in the network. Okay. So this is the resulting least cost path that you get from U. Okay. So correspondingly, if you have to write down or update the forwarding table in U, you can update it like this. If your destination is V, then your outgoing link should be U comma V. If your destination is X, it is U comma X. If your destination is Y, okay, if your destination is Y, so you can see that the least cost path that we had got was U to X to Y. So if somebody is arriving at U and it has to reach Y, so the corresponding interface should be U comma X, right? Similarly for W, again for W also, you were moving from U to X, then X to Y, then Y to W. So if somebody is arriving at U and is destined for W, the interface that they have to go out through is U comma X. So the corresponding outgoing link will be U comma X. Okay. So this is how the forwarding table will be updated using Dijkstra's algorithm. All right. So this is what I've already told. Now let's do one more example of Dijkstra. So this is the graph that you are having. So this is the starting node or the source node U. All right. So anyways, I will not do this. Can someone tell me what should be the shortest path from U to all the other nodes? Just try to find out. This is the first step. Okay. So just check and then tell me what should be the path from U to all other nodes. Just apply, implement Dijkstra's algorithm. So we already have direct connections from U to V, U to W, and U to X. So it is 5, 3, and 7. Okay, rest Y and Z will have infinite cost. Okay, so now what should be the next node that you will consider in
W.
Dijkstra? Now what should be the W, right? So now U
W.
to W. Huh. So U to W is 3 comma U. That's the minimum one. So you put W in N dash now. And now from W you will find out that its corresponding directly connected nodes. What is the cost for that? So you will check from W to V, W to X, and W to Y. Okay. Now, so what should be the cost in that case?
V.
For V, tell me what should be the cost now?
6.
6 what? 6W,
6.
right?
Yeah.
6W. 6W. Then for W, okay, W is anyways taken. Then for X,
It stays the same.
X it stays the same. Why? Because if you go from U to W to X, the cost is 7, which is higher than 5. Right? Then for Y,
11 comma W.
11W. Yes. Now here, which one will you choose? X, 5U. Right? So that's the minimum. So you choose that one. Okay. Now, from X, which all can be directly connected? Okay. So find out the costs, corresponding costs. V for V, what will happen? For node V now, what will happen? Anybody? V is not directly connected to X. So we will not go ahead and check that. Right? What is directly connected to X? W, Y, and Z. W has already been visited. So you are left with Y and Z. So what should be the cost for Y?
12 by X.
12. Okay, wait. If anybody, okay, wait. I was just checking. All right. Huh, wait. For X, somebody said 12. No, no, no. See, U to X, X to Y is 12, definitely. But if you check this, what was the earlier cost? From W, if you go to Y, it is 11. That is U to W, W to Y, which was there in the last one. So that is less than 12. So that is why we are going to take it as, or we are going to keep it as 11, comma W. That means if you want to visit Y from U, it is better to visit via W than via X because it is going to cost you more. Okay. Now to Z, if you want to visit, okay, so X to Z is 9 and U to X is 5. So that is 14 comma X. Okay. Basically, there was no direct connection from Z from the given node, that is W to Z. So it was infinite only. Now here, what's the minimum? 6 comma W. So now what will be the value, corresponding values? So V is directly connected to Y, which is not there in N dash yet. So what should be the value for that, for Y?
10 comma V.
10
10
comma
comma
V.
yes.
Yes. Okay. And of course, Z will remain 14 comma X. Even though there is no direct connection from V to Z, but we have already traversed it via x. Okay, with a minimum cost 14 comma x. Now among these, now y will get into n dash, right? Because it is having the minimum cost. So now y comes, you have traversed y, and then what's the direct connection from y? You have x and you have z, right? But x has already been visited, so only z remains. So now what should be the value here for dz here? What should be the
12,
value?
comma
12 comma
1.
what? Y. How are you getting that? U to W, W to V, V to Y, and then Y to Z. That costs you 12, right? Now it's done. All the nodes are visited, and this is what is your least cost path. Okay. So from you in this particular graph, all the for if you have to reach all the other nodes via shortest cost path, then this is your path. Okay. Okay. Now some notes have been given here. That is, um, you can construct least cost path tree by tracing predecessor nodes, and the ties, there can be ties when you are trying to find out the cost, but they can be arbitrarily broken depending upon whatever method you are trying to use to break the ties. Okay, so that's, anyways, we should not be concerned much on this one. Let's just check the complexity.
Excuse me,
Let's
ma'am.
just, yes,
Yes, ma'am. It is Saurabh Kumar. Ma'am,
yes, sir.
will you please take the attendance for today because only organizer can take the attendance.
Yeah, where were you? I was, there was no this thing that had started. Okay, anyways, it's already done. I'll stop the recording. Um,